So now we're going to consider what happens if you have a distance from a point to a plane. So what's the figure we should have in mind here? The figure we should have in mind, you've got your plane, and you've got some other point, which I'm calling P1, x1, y1, z1, and I want to know what that distance is between the point and the plane. Here's the idea. Suppose that you've got some other point, which I'm going to call, I'm going to call this point P naught, x naught, y naught, z naught, right? That's some other point that's sitting on the plane. It's any other point on the plane, actually. And I'm going to make another vector. The vector that I'm going to make is this vector b, going from P naught to P1. And finally, last but not least, I'm also going to make a new vector, which is just the normal vector. I'm going to call that n, right? And if you watched the recitations from Friday, the second recitation session, then this is going to start to look a little familiar. We gave you some of those challenge problems were very similar to this thing that we're looking at right now, trying to find what the distance from this point to this plane is. What are we going to do? We're effectively projecting onto P1 for finding this distance, right? That's what we're doing. We're projecting the vector b onto n and finding this distance as a result. So in other words, it turns out that this distance is the magnitude or the absolute value of the scalar component of b onto the vector n. If you unravel that, what does that give you? That's going to give you the magnitude of, or the absolute value of n dotted with b over the magnitude of n itself. You can unravel that a little bit more, and what that's going to give you in this case, n dot b, that's going to be the absolute value of ax1 minus ax naught plus by1 minus by naught plus cy1 minus cy naught all over square root of a squared plus b squared plus c squared. Now, you can take that a step further and write this as, now ax naught plus by naught plus cz naught, all that stuff, that's all going to come out to negative d, right? So another, or d rather, right? So just using the fact that x naught, y naught, z naught is on the plane, we know that ax naught plus by naught plus cz naught is equal to negative d, going from the equation for the plane that we had to begin with. So in other words, this whole thing comes out to magnitude ax1 plus by1 plus cz1 plus d over square root a squared plus b squared plus c squared. Now, I'm showing this to you in the interest of completion. I don't like using this equation. I really don't like using this formula, and the reason I don't is because to me this is just another friggin' string of symbols to memorize, and it's clunky and ugly, and I don't really understand, what I don't look at that, and I don't necessarily understand where that's coming from. I very much prefer just using comp. It's factually a smaller string of symbols to remember, and it gives you a little bit of a better idea about the geometry of where all this is coming from. So personally, I prefer that strategy. But that's just me. You can use either one, they're both fine, but I generally prefer using this boxed green thing. Okay. Oh, come on. So, and that's the same remark that I just made. So I'll ignore that. Now, what if you want to find the distance between these two planes? And so how do we, so first of all, before we even begin addressing this question, how do we know that these planes are, how do we know that we can even talk about this question in the first place? So why is this distance not 0? So why don't these planes intersect or coincide? Why do these planes not intersect? Can we see the answer to that question? Well, to answer that question, let's look at the plane equations. Here's the first one, right? So here's the first plane equation. Here's the second one. And we notice that the first normal vector is 10 to -2. The second one is 5, 1, -1. These vectors are parallel, which means that the planes are parallel. So since n1 and n2 are parallel, that tells us that the planes are parallel. And that's fine, but doesn't mean that they don't intersect. They could, for example, coincide. So they're not going to, if they intersect, then they actually are going to be the same plane. So are they the same? And no, they're not. And the reason why they're not is because we can see, for example, that that 0, 1, 0 is on the second plane. Right? Plug in 0, 1, 0 in for x, y, and z. 5, 0 plus 1 minus 0. That's going to give you 1. So 0, 1, 0 is on the second plane, but not the first. So in other words, this is a reasonable question. We really are looking at a scenario where we've got two different planes and they're parallel, but they're not the same. So we can actually talk about the distance between them, which is good. That's because otherwise I'd be asking a really ridiculous question in that case. So let's keep going. Let's look for the distance between 10x plus 2y minus 2 is equals 5 and 5x plus y minus z equals 1. So so let's just give like a rough idea of what this thing looks like. Here we'll have this be plane, we'll call that plane. Here we have plane 2. We'll call this plane, I'll call this plane 1, and this will be plane 2. And I'm going to draw it like this. So here's plane 1, and here's plane 2. And we know that the normal vectors are the same, so we still have that. Here's n. In both cases, we can take n to be 5, 1, -1. In this case, I'm trying to draw that it's going through the plane. We're going to need a point on plane 1 and a point on plane 2. So let's take a point on plane 1. Here's a point on plane 1. A point on plane 1 is, for example, let's call this A. We can take the point A to be any point on plane 1 that we want. Let's take, for example, 1/2, 0, 0. That's on plane 1. And what about a point B that's on plane 2? We can take B. We already said the point 0, 1, 0 is on plane 2, so that'll do. So we can take the vector between them and call that B, little b, with the vector. Little b, in other words, is going to be the vector that's given by 1/2, -1, 0. That's on the plane. Or that's a vector between 2 points on the plane. And we can take the vector n is 5, 1, -1. So we're basically ready to do what we have to do. So the distance is the scalar component of b onto the vector n. Or in other words, n dot b over magnitude n. Absolute value of n dot b in this case is 5 halves. So 5 halves minus 1 plus 0, 0 times negative 1, over root 25 plus 1. In other words, 5 halves minus 1 is, in other words, going to be 3 halves over root 27, or in other words, 3 over 2 root 27. You can clean that up quite a bit, by the way. Usually we don't really care too much about the right formula, or not. Well, we care about the right formula. We don't care about like the cleanest numerical expression, but you can make that a lot cleaner by writing this as 3 over 2 times 3 root 3, or in other words, 1 over 2 root 3, or in other words, root 3 over 6. I think that's the cleanest way of doing it. That's the distance. That's the distance between those two planes, is root 3 over 6. And we can now see where that's coming from with this very nice scalar component formula. Now, can you do that with the formula from before? Sure, you can, but I prefer not to, because I think this is just easier for me to see where all this is coming from. And a lot of students who've tried doing it this way with the scalar component formula tend to have more success. Okay, so if there are no questions, so what about the so what if we want to find these skew lines? Right now we have these skew lines from before, and I want to find the distance between these lines. Now this is a trickier problem. This is a little bit trickier than finding the distance between two planes, but we can do this. There's a way of doing this. There's a trick that we're going to use. So here you've got our two lines. Here's, I want to make it a little more line-like. Here's L1, and here's L2. The trick basically is to find the distance between these by finding a plane. So here's the distance between them that we're interested in, assuming that's the minimal distance. The trick basically is to find a plane that contains L2 and a plane that contains, but that doesn't contain the plane or the line L1 and never actually intersects it. So that's what we're going to try to do. We're going to try to find this plane that contains, that contains L2, and we're going to find the distance between this plane and L1. So see what we're getting at here. This is the image that we should have in our minds at this point. Okay, so let's keep going. So how are we going to do this? So just to draw the figure again, we've got our weird line. Come on. There we go. So there's L2. Right, so that's one line that we're interested in, and we're also interested in this other line that's going, okay, I'm going to try this one more time. Here's L1, and here is L2, and here's the plane that we care about. And so what are we going to do? We're going to find that this distance here, here's a point on, so what do we need? We need a point on this plane, could just be a point on L2, and we need a normal vector for that plane. So here's the normal vector that we're eventually going to use. Well, a point on the plane, that can be done by just finding a point on L2, right? Since L2 is on the plane. So just take a point on L2. And we know that L2 is described by the parametric equations x equals 2s, y equals y equals 3 plus s, and z equals -3 plus 4s. And what that tells us is that a point on the plane can be the point 0, 3, negative 3. Is on this plane. It's a point on L2. It's also going to be a point on our plane. What about the normal vector? Well, the normal vector, n, we notice that n is orthogonal to L2. But if you think about that for a second, we also realize that n also has to be orthogonal to L1. We see that? And why is that? Well, one concrete way of seeing that is L1 is parallel to the plane. So L1 is parallel to the plane. You can think about the direction vector being actually inside the plane, so n is also going to be orthogonal to L1. Now L2 has now just to remind ourselves, L1, which is given by x is 1 plus t, y is negative 2 plus 3t, and z is 4 minus t. So, with all that in mind, we know that n is orthogonal to both v1, which is 1, 3, negative 1, that's the vector for L1, and v2, which is 2, 1, 4. Cross product time. We can say in that case that n is just the cross product of v1 and v2. It's I, j, k. 1, 3, negative 1, 2, 1, 4. Going through all that, I is going to be, so 3 times 4, so 12 plus 1 is going to be 13i. J is, so minus 4 plus 2, so minus 6j. 1 minus 6, so it's going to be minus 5k. Now, actually, doing all of that will give us 13 plus 13 minus 18 plus 5 is 0. 26 minus 6 minus 20 is also 0, so it works out. That's our normal vector. So that's great. So we have, in other words, a normal vector. We know now that n is going to be 13, negative 6, negative 5. That tells us what n is. We're almost done. Now all we need is a point on L2, or sorry, L1. All we need now is some other point that's on L1. We have a point that's on L1. The point on L1 that we can use, well, just take the point that we're given on L1, which is, in this case, the point 1, negative 2, 4. Right? That point is on L1. That's coming just from the parametric equations for L1, 1, negative 2, 4. So in other words, we now know what we're going to have to do for B, and then we're just going to project as we usually do. So to, do I have another slide here? I think I do. Yes, so the, so just to summarize everything that I've just said, that we're talking about here, I'll make a big picture here. So here's L1. Here's L2. Here's the plane that we have just constructed. A bit of a weird looking plane, but that's how it goes. And we know that we're looking for this distance, which we know is given by, which we know is going to be orthogonal to this normal vector. N is 13, negative 6, negative 5. we know that on the bottom side here, we've got this 1 point, which is 0, 3, negative 3, coming from the formula for L1, and we found that we also have this point, which was going to be 1, negative 2, 4, coming from L1, gives us the vector B between them. And now it's even more clear that all that we're doing is just projecting, using just scalar projections, onto this segment. So the distance that we care about is the scalar projection of our vector B onto n. What is the vector B, by the way? Vector B is going to be 1, negative 2 minus 3 is negative 5, 4 plus 3 is 7. So in other words, that's going to be the magnitude of 13, negative 5 times negative 6, so plus 30. 7 times negative 5 is minus 35. Right? Over the magnitude of the normal vector, which in this case is 13 squared is 169 plus 36 plus 25. And just doing all of that calculation, it's 43 minus 35 comes out to 8. So it's going to be 8 over square root of 169 plus 36. 170 plus 35 is 105 plus 25 is 230, I believe, after doing all that. So that's our formula for the distance. That's our distance between these 2 points. And I'm not going to bother really with cleaning that up any, but that's basically what we have. So thank you everyone for are there any further questions on anything that we've done today? And if not, then I will end here. And oops. So, and we will continue our discussion tomorrow.